when we were trying to find the point on the curve that was closest to the origin, we knew it was optimization because it said superlative case. And to maximize closeness, we minimize the distance. So this is the second example we saw like this. For these distance problems, the endpoints are usually going to be meaningful, meaning you can't just discount them and look for the open interval solution simply because this is not a geometric shape. For those geometric shape problems, of course, the endpoints don't make sense because you've collapsed your shape down to nothing. So we were looking at this diagram here. The parabola is in purple. The closest distance to the origin, we established a nice interval for x in which our distances could live. If x were 0, we would be at the high point, which is 1 unit away. If x were pi halves, we'd be on the x-axis, which would be pi halves away. And any x value that was, to the right of pi halves wasn't going to work, or for that case, to the left of negative pi halves. We also noticed that by symmetry, I can work in this little quadrant 1 area. And if I find an x value on the open interval between 0 and pi halves, there would be a twin on the other side that is just as close to the origin. All right? So that's what we're doing. We know that the right endpoint here of our interval pi halves is not going to be the answer because pi halves is a little bit bigger than 1. But the question was there an x value on the interior that was a little bit closer? On the previous example with the parabola, the critical value was the closest point. So we got down to the derivative equaling 0, which was this, and this is where I said you would need a calculator to help you solve it. And so this is what we get. We type in our function into y1, 2x minus sine of 2x. We make sure we're in radian mode, which I am, and graph 0 and y2 or y3 or whatever. This is one of the 3 big things we're going to do with our calculator, solve equations. Now, when you're working on an interval, make sure that you set your x min, x max to that interval so that you are looking for just the information you're interested in and you're not tempted by outside information. Now, typically, what I tell you for your y min is to say -3 to 3. That typically does a good job because it stretches out your y-axis enough, but it still keeps the x-axis right in the middle. And it's not too small that you just see vertical lines. You still see curvature. But in case it hugs the x-axis or something, you don't have to waste time. All right, so here we go. If we hit graph, and this is what I mentioned in class as you were walking out, hopefully there's a critical value. Hopefully there's a critical value on the interior, and my graph would change from negative to positive there because that would make that x value not just a local min, but on my relevant interval, it would make it an absolute min, right? And that would be the x value that would be closest to the origin. So here we go. We're looking for something like that. And the calculator gives us something that looks like that. Now it is going to show the x-axis coming in here. Now notice it appears to be positive. I've already stretched it out, but it could be doing something in here, right? It could be that it crosses and then, or is negative and then crosses, but it's just so close to the x-axis. In a -3 to 3 window, this typically works, but what I'm going to have to do now is get kind of serious. How about -0.01 to 0.01? I graphed R prime. I graphed R prime. And here's what it looks like when I really stretch it out. So again, notice right there, it looks like it almost starts negative and then crosses, yes? Well, at this point, you could go second trace number 5. If it does go from negative to positive right in there, your calculator should be able to detect it. So second trace 5, first curve, there's my derivative, right? 2x minus sine of 2x. And then 0 is the second one. And for your guess, you can just hit enter. And then it says error, no sign change. What does that mean? That means the calculations are not detecting a sign change to give an estimate result for the allowed number of iterations. Now, if there's no sign change, that means that it doesn't start negative and go positive. It's actually positive the whole time. Which means what? How many critical values do we have then? 0. Okie dokie. So let's come over here. There are no solutions to this on the interval from 0 to pi halves. So there's no critical values. And that means what? Does that mean that there is no point on the curve that's closest to the origin? Preposterous. There has to be a point closest to the origin. It's just not going to happen at a critical value of our interval. It has to be at one of the endpoints. Well, now we kind of know the answer then, don't we? If it has to be one of the endpoints, and our endpoints that we came up with are 0 and pi halves, we know at 0 it's at the high point, which is 1 unit away, and at pi halves it's pi halves units away, which is greater than 1. So what's the answer? Well, let's see what the question was asking. Did it want the distance or the actual point? It says to find the point on the curve that's closest to the point 0, 0. So the closest point, here we go answering it, the closest point is 0, 1. Yeah, 0, 1. Now, I think you can kind of see or argue that depending on how steep the graph of cosine is, there might be a point that, if this thing kind of came down very rapidly and went like that, there might be a case where maybe the right endpoint would be closer than the y-intercept, yeah? Or something maybe on the interior. It all depends on the severity of the curve. How fast is it increasing and decreasing, and also where is that point? So in this case, the endpoint is the answer. There is no critical values. Sometimes you might get a critical value and the endpoint is still the answer. But 99 times out of 99.5, especially for the problems you will see, the critical value, the one critical value that you get on the interval should be the answer. Just be aware that it is a possibility for these types of problems where you're trying to find the closest point to. Okay, so I feel better if we would have stopped there on Friday, but it is what it is. Any questions on that one? Okay, this makes a good quiz question tomorrow. Find the largest rectangle that can be inscribed under the curve of y equals 16 minus x squared in the first quadrant. Is this optimization? Yes, how do we know? Largest rectangle. All right, is this one for which we can draw a picture? Yeah. You're not going to be graded on your artwork, but sometimes drawing a picture is helpful to orient yourself to what you're doing. Okay, so it says the largest rectangle that can be contained under the curve in the first quadrant for this graph, y equals 16 minus x squared. That's a parabola that opens downward. We know that. Has a y-intercept of 16. What's its x-intercept? 4 and negative 4, so you can set it equal to 0 in your head very quickly. And we're going to be staying in the first quadrant, so somewhere in there. Now, I want to figure out essentially the largest rectangle. So we'll give the dimensions and its area. I don't know where it's going to live. It could be up here, or it could be down here, or it could be somewhere in the middle. Now, what I do know is to maximize the space allowed, 2 of its sides are going to have to be on the axes. Would you agree? And that other side, the vertex in the upper right corner, is going to have to be on the curve. If I stop short of the curve, then I'm not increasing it as big as possible. And, of course, I can't go past the curve. I don't know which of those 3 are going to be the right answer. It may be like none of them. It may be that one. So I can just do trial and error and start randomly drawing, or I can do something a little more systematic, which is what I'm going to do. So what I'm going to do is draw just a representative solution right there. Now, this is going to be a point on the parabola. I'm going to call it not x comma y. Well, I'll call it x comma y. Might as well. When you do that, though, you get the width is x and the height is y. So defining the point on the graph also gives you the dimensions, essentially, of your rectangle. Okay, so here we go. We're trying to find the largest rectangle. So what is it that we're trying to optimize? Area. Good. So we're trying to maximize the area. So here we go. The area of my rectangle A is going to be x times y. Everyone okay with that? And what's preventing me from making it infinitely large? Well, the fact that it has to stay under this curve here. So this is your constraint equation. And you can substitute that in there. Since it's already solved for y, you get 16 minus x squared. And you could have jumped straight to that if you want. As I mentioned last Friday, you could define this point on the curve, not just x, y, but you can define it as x comma 16 minus x squared. And then you have y already in terms of x. But it's not a big deal to do that. So there's your area equation in terms of x. Once you have it in terms of a single variable, this is a good time to be thinking of a relevant domain. Now, we do have a geometric shape we're talking about here, a rectangle. So typically, endpoints don't make sense for geometric shape. What would be the absolute smallest x could possibly be? 0. If x were 0, what's happening to your rectangle? It's collapsed down to nothing, to a width of 0. So I think 0 is a safe lower bound. And what would be the biggest x could be? 4. Now, if x were 4, what's happening to the height of that rectangle? It's going to 0. So I should have a 0 area when x is 0 and when x is 4. But some x value then between 0 and 4 is going to give me a maximum. And I know it's got to be there because to go from 0 to 0 through positive areas, it's got to go up, it's got to come down, right? My area has to go from nothing to something to nothing again. So there's a max in there somewhere. So our relevant domain is going to be 0 to 4. And we know it's going to be there. We know it's going to be an absolute max. So we just need to find the critical values. So what I'll do is distribute, and I get a cubic. Okay, now a prime would be 16 minus 3x squared. If I set it equal to 0, I'm not interested in the critical values where it's undefined. Not that this polynomial ever is. I get 16 equals 3x squared. X squared equals 16 thirds. And if I take the plus or minus square root, I get the square root of 16 over the square root of 3. 4 over the square root of 3, yeah, or 4 square root of 3 thirds, however you want to write it. Now, do I want both of those in this case? I just want the positive one, all right, because I'm in quadrant 1. Now, let's see if we can figure out what the graph of the cubic looks like. The cubic is going to have a negative leading coefficient, so it's going to look something like this. There's 4, and looks something like that. That's what the cubic looks like. So notice the domain of the cubic polynomial is all real numbers, and the range of the cubic polynomial is all real numbers. But in our little relevant world right here, we're looking at just this part of it, where the area is 0 when x is 0, and the area is 0 when x is 4. Because we're looking at this part of the graph, we know it's not only going to be a local maximum, but also an absolute maximum, because a prime is positive. Let's go ahead and write that. Let's go write that. Area is maximized. This will be the first time we're actually writing it out. Area is maximized when x equals, I'll use 4 over the square root of 3. Since, and here we go. We're going to kind of do like a local argument, but we got to add that global flavor to it. So how about since a prime is greater than 0 for all x, now when you say less than 4 square root of 3, that would be a lie, correct? But you could say less than 4 square root of 3 and greater than 0. That means for all x on that interval. That's on our relevant domain. And similarly, a prime is less than 0 for all x. You'd have to be careful if you said greater than 4 square root of 3. Although that would be true. you still want to go ahead in this case say less than 4. So essentially, everywhere to the left of the critical value on our relevant domain and everywhere to the right of our critical value on the relevant domain, our slopes are positive and negative respectively, which makes it now a global argument. The words for all turn it from a local argument to a global argument. So if you did have to justify, that's what you would write. Okay, so now we answer the question. We know at least the x dimension, so let's go ahead and find the dimensions. So the largest rectangle is x equals 4 over the square root of 3 by y equals, and how do we find the y value? We plug it back in up here. So let's do that. We get 16 minus 16/3, which if you wanted to simplify that, that's, is that anything nice? 32/3. 48 minus 16. What's that? That's okay, good. So that would be the actual dimensions of it. The question would be a little bit more specific, like find the dimensions of or find the area of. If we wanted the actual area, now that we have both dimensions, of course, you can multiply them together. Keep in mind, though, that once you find that critical value of x, the two equations that you might be using are the original constraint equation, and in this case, that's what we did to find the other dimension, or you could plug it back in up here, which would give you the area in terms of that value alone, without having to necessarily specifically find the other dimension. All right, so if this were a quiz question with justification, you could handle it, right? Tomorrow? The math is not that bad. Okay. Yeah, this is your justification. And you don't want to offer up a justification if it doesn't say to. What's the most common error that students make when they're justifying? A lot of them realize it has to be a global, so they'll say the words for all, but they'll say for all x less than that, and they'll say for all x greater than that. And that's not right, is it? This one technically is not wrong, because our slopes are negative on this parabola everywhere to the left. But if you just say this, that the slopes are positive everywhere to the left, they're not, right? Because they come in negative here, and then they're positive there. So you have to say that they're positive everywhere on the relevant domain. And usually there's a lower bound. So you just need to make sure of that right there. That's the one thing to remember. Okay? And that right there would get full credit. You're not staying within your relevant domain on the upper end, but you're not saying anything wrong either. All right, we'll practice justifying as we move forward here in the rest of these. Okay, example 8, an open top box. Hey, it's Christmas time. You might be constructing these to put your Christmas gifts in. No, an open top box, you'll just use what? The gift bags, right? That's the modern day open top box. Well, we're going to make an open top box virtually here, constructed from a square piece of cardboard that's 3 feet wide by, I guess, what would be the other dimension? 3 feet long. Okay. By cutting out a square and bending up both sides. This is a classic optimization problem. What's the largest volume that the box can have? All right, so here's the idea. Take a square piece of cardstock or whatever that's 3 feet by 3. And you are going to cut little corners out so that you're left with these folding lines right here. And you're left with this. Oops. And with those corners gone, then you can fold up the sides, and you have your open top box, right? Looks like that. Now, we want to be able to put as much stuff in our box as possible up to the rim. So we want it to have the largest volume to hold the most stuff. And of course, we only have one 3x3 piece of paper. I guess we're going to use sticky tape on the corners, maybe. We're not going to use extra material to hold it together. So sticky tape works better than non-sticky tape for that purpose. But we don't want to have to build this and then measure it and say, oh, that wasn't the optimal size. So this is optimization. First thing first, we need to write an equation for what it is we're trying to optimize. We're trying to really maximize the volume of a rectangular prism, yes? What are the dimensions of a rectangular prism? What do you want to call them? Length, width, and height. So there's our optimal equation. The only problem is we need to get that in terms of one variable, either L or W or H. We have it in terms of three variables. Oh, I like that. That takes care of one of them, right? So which one do you want to use twice? L? Okay. So L squared H? I like that. That's better. Will it be L cubed, though? Maybe. It might be. Maybe the most optimal rectangular prism is a cube if we were using material on all six sides. But if we have an open top, that we might be able to use some of that material elsewhere. So yeah, that kind of changes things. Well, no, we're cutting squares from each corner. Yeah, that's what's important. So if you want to say, do you know how much we're going to cut from each corner? No. So if you want to back it up and say that you're cutting actually X from each corner, that was kind of in the instructions there. Kind of subtle, but yeah, we are cutting squares from each corner. Now, when you fold up the sides, let's see, in terms of X, this is one of the dimensions and this is one of the dimensions, right? And they should be the same. What's the new length? If it started as 3 and we took an X from each side, it should be 3 minus 2X, right? By 3 minus 2X. So we can actually say that it's going to be 3 minus 2X by 3 minus 2X, or 3 minus 2X squared. And what would the height be then? When you fold up these little tabs, this little X tab, doesn't it become the height? If you imagine folding it up, it becomes the height. So there you go. So you can actually, if you think about it that way, X is the amount you're cutting out from each corner, you can almost go straight to your primary equation, which is in terms of a single variable, and it already has the constraint built in. That's the 3 minus 2X. All right, so there's your primary equation. Constraints already taken into consideration. So let's think of a reasonable domain. What's the absolute smallest we can cut? 0, right? 0 is a safe lower bound. But if you cut 0 from each corner, what's the volume of that flat 3x3 sheet of cardboard? 0. So that's going to be an absolute minimum because you haven't done anything to it. So I know it's going to have to be something bigger than that. And what would be the absolute most I could cut from each side of a 3x3? Yeah, 1.5 or 3 halves? Because I'm cutting it from both sides. Now, what's going to happen to my material if I cut 1.5 from both sides of 3? It's gone. I've obliterated it. I've made basically 4 squares out of the whole thing, and there's nothing to fold up. Yes? This whole thing up here is 3, right? If I take out this little X right here, and I take out this little X here, I'm left with 3 minus 2X. Yep. Okay, so what I know then is that somewhere between 0 and 1.5, I know the volume is going to be equal to 0 at 0 and at 1.5. But somewhere in between there, I actually have something I can work with. It's going to be a positive volume. So I already know that it's going to be an absolute max on that interval. Even though my volume equation ends up being an x squared times x, it's a cubic polynomial. Volume is a cubic polynomial. Makes sense, I guess. I need to find the critical values. You want to use the product rule, or do you want to expand it all out and use the power rule? I need the critical values. Let's use the product rule, huh? Here we go, B prime. The first factor is the chain rule, actually, first, right? 2 times 3 minus 2x to the first, times the chain rule, a negative 2, times x goes along for the ride. plus 3 minus 2x squared times the derivative of x, which is 1. Okay? Now, when something is partially factored, if you have multiple terms and they're partially factored, don't just start expanding it out and combining like terms. Look to see if you can pull out a common factor. And I see that there's at least a 3 minus 2x that I can factor out of both of them. And that leaves us a negative 4x in the first term. You'll see that? And in the second term, I'm left with just a 3 minus 2x to the first. Because I took one of them away, I'm just left with one of them times 1. I don't even need the parentheses anymore. If something is partially factored, multiple terms, look to factor out common factors first. And now on the inside there, I can clean up what's left, and I get a 3 minus 6x. And that's equal to 0. So if I set each of them equal to 0, then I get 3 equals 2x, and x equals 3 halves. Or I get 3 equals 6x, and x equals 3/6, which is a half. I guess both of them work, huh? The first one doesn't, right? In fact, that's our upper bound. That's the one that obliterates the box, right? You cut out 1.5 inches from both sides of a 3-inch thing, and you have nothing left. So this doesn't work. Now, that doesn't mean that the cubic polynomial doesn't have a horizontal tangent there. In fact, it does. We're just looking for our critical value, which is 1/2. So from there, we can actually curve sketch a little bit. If we're trying to figure out what the volume function looks like, it's going to be a cubic polynomial, and it's going to be something like this. It's going to look something like that. We know that this is 0. Here's your first horizontal tangent, which we just found out to be at 1/2. The second horizontal tangent, was at 3/2. And that's where, so it actually bounces off the x-axis there. And there's your volume. But notice, we're only interested in this right here. So beyond 3/2, notice we still have positive volumes. They still make sense in the sense of volume making sense, right? We can have positive volume. But unfortunately, they don't make sense in the constraints of our problem because it requires having a piece of cardboard that's bigger than 3/2. So there you go. We know it's an absolute max on x equals 1/2. Let's go ahead and write the justification one more time. X equals 1/2 maximizes V, and I can use V because I referred to it up here. I defined it. So it maximizes V. You could say absolutely if you want. That's a nice little adverb, right? How does it maximize it? Absolutely. But you don't need to because we assume that, right? Since V prime, which we computed V prime, so we can refer to it. We don't have to say the slopes of V. Since V prime is, see, it's going from increasing to decreasing. So V prime is greater than 0 for all, and then here's your inequality. 0 less than x less than 1/2. And V prime is negative for all, and then from 1/2 to 3/2. 1/2 to 3/2. Now, if you didn't put your upper bound there at 1/2, you would lose points, right? Because it actually starts increasing again. If you didn't put your lower bound at 0, would you be saying anything wrong? No, because this slope is positive all the way up to 1/2. So here you wouldn't lose points if you didn't have your lower bound because technically it's a legitimate argument. But I probably meant 1/2. No, I did not. No, times 3. Yeah. No, that's not running through the tape at the end of the race. It's running 26 miles in the last 0.2. You give in to the free beer sign at the finish line. You're not at the finish line. You're not at the finish line. Yeah, it's near the finish line. Yeah. It's a free beer sign. They try to tempt you at the end. Or finishing shirts, $5 right there, like at mile 18. Anyway, there you go. So what makes this a global argument instead of a local? For all, right? You can, yeah. I was not ready to leave this yet. So you could actually, not with that, you could do this. You can write that. That works nicely as well. What if you didn't write that? What if you just said for, I'll get used to this iPad thing soon enough. What if I just put for and I didn't say for all, but I gave this interval? Would that still be okay? Yeah, if I just say for x between 0 and 1/2, it's kind of understood that we mean which of those values between 0 and 1/2. All of them, not just selected or favorite ones. So it is implied. But I would like for y'all to write the word for all or to use the symbol, because why? It reinforces the fact that you're making a global argument from what we've learned originally as a local argument. Okay, example 9. I think we have time to... No, I never did. No, and that's the moral of all these stories. In the end, answer the question. What are we going to put in the open top box to give to someone? What's the largest volume? We want the actual volume. How do I find the volume? I have x equals 1/2, and now I need to figure out the volume. We have two options. You can figure out what all the dimensions are and multiply them together, or you can simply come back up here and plug it into that first equation you created that was in terms of x. So let's do that. So now that we know that it's going to be the value that maximizes, we do answer the question. So the maximum volume is 3 minus 2 times 1/2 is 1 squared times x, which is 1/2, which equals 2 squared is 4, 4/2 is 2. And what would the units be? We're talking about feet, so this is volume supposed to be cubic feet. So if you were to fill this box, this open top box, up to the brim, it couldn't like go above. Just filled it completely. You could fill it with 2 cubic feet of stuff. Yeah. Good question. No. No, you don't need them there. Doesn't hurt to have them though. Doesn't hurt to have them, but you would not lose points, huh? It does if they're wrong. That's true. Yeah, if you put inches there, and then it would be wrong. Yeah, that's a good point. I like that. Yeah. Okay, cool. Now, if we needed to build the box, of course, we can figure out what the dimensions are. It's going to be 1/2 by 2 by 2. Okay, soda can. Let's see if we can get through this one quickly. You ever wonder why the soda can is the shape and size that it is? You never have? You think it's just random? Like, that's what fit in the machine? The machines were there, and they were like, well, this fits into the Coke machine nicely, so maybe we should put Coke into these cans that fits into these machines nicely. What came first, the Coke machine or the Coke can? I don't know. No, these are highly engineered, and they have evolved quite a bit. They've evolved over the years. But once they realized that portable carbonated beverages were going to be popular and people were going to like them, they wanted to mass produce them. And they wanted them to be portable, right? They wanted it to be cheap. So that's why they kind of use aluminum. Pretty plentiful and pretty inexpensive. But they also needed it to have other features, right? And there's a lot of different features. But any first project, before it gets turned over to the marketers and the people that have PhDs in feng shui, They're turned over to the engineers, and the engineers come up with kind of like this jumping off point, if you will, for the most optimal can for packaging, okay? And what are we trying to optimize? Well, let's read. A cylindrical aluminum can is to hold 12 ounces of tasty beverage. Now, believe it or not, a lot of research has gone into that number as well. What does the average person enjoy drinking in one sitting? Well, if you're one of my kids at home, it's not 12. It's not 12. Because you open a can, you leave it sitting out, and it goes flat, and the next day it's still 3/4 full, and you do that all the time. Okay? But most people, what are the dimensions of the can that are going to minimize the amount of aluminum used? There you go. You want to minimize the amount of material used, again, in the interest of increasing your profits, right? If you use less material to make it, then you can sell it for a certain amount. That's all profits that you reap. So it has nothing to do necessarily with trying to save the earth, right? Let's use as little aluminum as possible to preserve the earth. It's probably more about optimizing profits. All right, so here's a hint. 12 U.S. fluid ounces equals 21.6562 cubic inches. That's kind of nice. If the dimensions of the actual can, and if you have a can and a ruler, you can measure them, but I've measured them. It's about 2.6 inches across and about 4.75 inches tall. That's about the actual dimensions of a current Coke can. Does the actual can represent the optimal can? Well, before we even start, do you think the actual can is the most optimal can there is? Why not? We'll talk about it later. We proved it last year. Yeah. This is a highly engineered can, and once the engineers give you the optimal shape, that's where the people come in and they're like, oh, well, it needs a little something over here. It's going to look nice. People are going to be like, ooh, you know. And anyway, so here's what we're going to start with. Here's a cylindrical can. A cylinder has essentially two dimensions that are important for its calculations. The radius of the top and bottom, and the height. This is a geometric prism, a circular geometric prism, and h is the distance between the two circles. Here's what you need to know. The volume of a cylinder is the area of the face, which is the circle, pi r squared, times h, the distance between them. Memorize that. We'll be using that kind of on and off throughout the year. Well, I need to get that now in terms of a single variable, either r or h. So what am I limited by? I'm trying to, well, let's actually write the optimal equation. That's not even the optimal equation. I need to minimize the aluminum. That's the first thing first. Minimize aluminum. Minimize the aluminum. Well, when we say minimize the aluminum, we say the amount of aluminum used in creating the can, which comes out to be which quantity? Surface area. There you go. So we're trying to minimize actually the surface area. So that's the equation I really need to start with. So let's call A for area and the surface area. Well, you're going to have the area of the top circle and the area of the bottom circle. And the area of a circle is pi r squared. But you're going to have how many of them? 2. So it's 2 pi r squared. That takes care of the top and bottom. And then plus you have what's called the lateral surface area. Lateral meaning side. So if you were to cut this can open carefully, with your parents' permission and help possibly, and you unrolled it, it would look something like a what? A rectangle, right? And of course, the height of the rectangle would be h, but the length of it would be what? The circumference, right? Which is 2 pi r. So the dimension of the lateral surface area, which ends up being a rectangle when you lay it out, would be 2 pi r times h. You do need to know the surface area equation for a cylinder, but I think it's probably one that's best just to kind of produce or think about as you need it. All right, now that's the one I'm trying to optimize right there. I'm trying to minimize it. It's currently in terms of both r and h, and I need to get it either in terms of r or h. I'm hoping to keep the r in there and get rid of the h. Would you agree? Just because I don't want to have to plug something in twice and square it. So I like to solve for h on the other one. My constraint is the volume, right? We have determined, or it has been determined, that it has to hold 12 fluid ounces, which is 21.6562. 21.6562. That is the required volume that it needs to hold. So we set the pi r squared h equal to that, and now we have our constraint equation. This one is easier to solve for h. It's also the one that I wanted to solve for to plug in, so that's win-win. So we get h equals 21.6562 all over pi r squared. And that's the one I'll come back to if I need to figure out the height at the end. But for now, that's what I'm plugging in over here. So here we go. We got the surface area is 2 pi r squared plus 2 pi r times h, which is 21.6562 divided by pi r squared. Now we could get a reasonable domain for r, but I'm going to go ahead and simplify it a little bit first. The first term, 2 pi r squared, looks harmless enough. But in this second term, once I plug in, there's some things that happen. The pi's divide out. That's good. One of the r's divides out. And I'm left with 2 times 21.6562 all over r. And I'm not going to even double that. I'm just going to carry it around as twice that. Right, 43 something. All right, now let's think of a reasonable domain for r. This is a geometric shape, so our radius can't be 0, can it? The radius of the can being 0? No. It can't be negative, so I know it's got to be some positive number. What's the upper bound based upon the volume? Who knows? All right, now that's good because notice again my equation has a r in the denominator, so 0 doesn't make sense in the equation. I need the derivative then. I need the critical values because there really are no endpoints. So the derivative of 2 pi r squared is 4 pi r to the first. And again, the second term, it's really r to the negative first. So we'll do it together in our head. R to the negative first. When we do the power rule, we get negative 2 times 21.6562. R to the negative second, which then we slide back down here and we get r squared. Now last time we had a problem like this, I went ahead and set it equal to 0 and we algebraically solved. But I'm not going to do that in this case because that's not necessarily the way that we want to go if we ever want to come back to the derivative. What I'm going to do in this case is what we did in the previous chapter, get a cleaned up, full-fledged factored version of the derivative, because we might need it for like some number line chart. So the first one, I'm just going to essentially multiply by r squared over r squared to get a common denominator. And that becomes 4 pi r squared times r is r cubed minus, and this one's already good. So a slightly better version of the derivative. And we'll end up with the same critical value that we would if we would just set this equal to 0 and split the terms. But now we want to know where a prime equals 0, which is coming down to setting the numerator equal to 0. And we're almost there. We'll divide through by 4 pi. And then, of course, we'll do what to solve for r? Take the cube root of that number there. And since the endpoints don't make sense, we know that when r is an absolute minimum, we collapse the can down to nothing horizontally. And when r is a maximum, we've crushed the can down so the height is 0. And that's just a flat disk. So somewhere between two endpoints that collapse it to nothing, there has to be this optimal value.
You need to make that 21 divided by 2.
Yeah. If you're looking for a simplified exact answer, 21.6562 divided by the quantity 2 pi. All right, so now with the help of a calculator, And that would be what units, maybe there, if we're just stating it as our final answer. Inches? Let's see what that is. This would be the answer, by the way, that the engineer would hand over to the department. Here you go. Huh. Thank you. I don't know why they talk like that, but they're very technical, right? Here you go. This is the exact answer. This is the exact answer. And they're not going to mess with it because it's irrational for a couple of reasons, right?